You can see the slides. Okay, this is just a recap. We went through this definition in the last session, but I thought because I was, I was in a rush, it wasn't well properly explained. Maybe some people were struggling. So I will just do a quick recap, because this is very important. If you get lost here, you will not be able to pick up some of the challenges that and the notions that we will be covering in the next few slides. Okay, so given a group, okay, and an element on a group G, small g, and an integer k. So we make this definition, okay? So we say for k equals 0, the power of g to 0, we say it's equals to the identity of the group, okay? So this E bold is the identity of the group. This is the convention that we are using here. By the way, if you pick in any book on group theory, they might use the symbol 1, so this is just convention. So this is for us at the moment, because we are working in abstract, we are using this E as identity. So that's the definition for the use case, for the case when k equals 0. Now, for when k is positive, this thing is defined like this, so g to the power of k is essentially like g times itself, k times. Okay, so you apply the binary operation, k times. Okay, I forgot to put k times here. I knew I forgot something. Okay, so that's for the case when k is positive. Now, when k is negative, we define it like this. Okay, essentially the power to the inverse of k. So the group inverse of g. So we define it on the group inverse of g. So we apply the binary operation k times to the inverse, to the group inverse of g. So that's it. This is the definition. Okay. Now, this is, I believe this is, you already done this before. That's why I'm not putting it here as a challenge. So these are like the properties of the group exponentiation. So, given two integers, k1 and k2, and an element of the group, these things here hold. I really challenge you to try to do this. You can actually see the property of the normal, the normal structures that we are used to, the normal groups, like in this case, this looks more natural on like multiplicative groups when we talk about them. In fact, I will comment in a minute when we deal with additive groups. There's a convention that we will do. Yeah, but this is like all familiar stuff with the likes. For example, imagine R, for example, or Z. Okay. And the first challenge I'll make today, as I told you, we'll have a lot of challenges, is this: whether if you have two elements of the group, if they commute, then we have this identity. Okay. So I challenge you to try to solve it, whether it's true or not. Okay, so now here's a very important comment, because it's very important to, I hope I won't confuse you. So when we deal with additive notation, say for example with the z plus, okay, the additive group of the integers, the identity is the zero that we all know, right? Okay, so the exponentiation, g to the k, coincides with the notion of multiple. Okay, so let's see what I mean with this. So for example, this thing when k equals 0, so this is by definition this is 0. So this is essentially means like the multiple of 0. 0 times g, right, equals 0. When we are talking about this concrete group here, this z plus. Okay. And the same when k is positive, this thing here is just like doing the addition, k times, okay, which happens to coincide also with the multiple kg, right? Because for example, let's take for example, let's say we are in this case we are dealing with this with the additive group z, right? 2 plus 2 equals 4. This is the same as 2 times 2, right? So it's a multiple of 2. Okay, so the reason the same with when we are dealing with the term with the negative also. Okay, with the I mean with the additive with when k is negative. So we are applying the term the negative, the additive negative. We are adding it k times. Okay, which also coincides with k times the additive inverse. Okay, so what I want to say is that this happens a lot in the books. That's why you might get confused if you pick up a book if you don't know this. This is so when the group is additive, you don't write this. You write this. So you take kg instead of k to the 10. We reserve this for when we are dealing with some sort of notion of multiplication, or if you want to be more precise, when we deal with multiplicative groups. Okay, so for additive groups, the convention is to just write this kj instead of this. Yeah, so this is just notation stuff that you need to be aware of. Okay, I hope I didn't confuse you. Let's see, no one is confused, so that's good. Okay, now a very important notion. This is very small, forgive me for the slide. This is because I have to insert this table here, but I hope you can see. You can see this slide, right? Is it clear, George, or just on the chat? Yes, okay. So the slide is clear, thank you. Okay, so when we have a group and an element G, we say the order. First of all, there is another concept of order that we defined in this last session. That's the number of elements of the entire group, so the cardinality of the group. Okay, there's also this notion of order for individual elements of the group. Okay, so we shouldn't mistake them, though you will see some in few slides. There is some connection between them in certain cases in the thing. Okay, so for the time being, the order of an element G is the smallest positive integer, such that when you take G to the power of that positive integer, you get the identity. Okay, so it's a positive, the smallest positive integer. Okay, and we write, coincidentally, the notation is also the same. So the order of the element G is also denoted like this. So the order of G equals n. Okay, so that's the definition of the order of an element. So it's the smallest. So you have to search, you have to check. I give you a concrete group, I give you an element of it, I tell you what's the order of the group. You go, you search, you see the smallest element, the smallest positive integer. When you take the power of the element G that I give you to that positive integer, if it yields the identity, then that's the order of G. Okay. Now, there is no guarantee that it might not exist. Okay. So if there is no such a n, positive n, we say that G has infinite order. Okay. We won't go much into technicality to why this and these things. You don't need to know this. Okay. So this is just a fudge, a hack. Okay. So when there is no such a n, we say the thing has infinite order. Okay. Now, do you all agree that the group identity E has order 1, right? Okay.
Actually, that's a bit ambiguous. The identity also has order 0.
Remember, this is positive. The n has to be positive.
Okay.
N has to be positive. Okay. Okay. Do we agree? So, there is our friend Soham agrees. Yes. Is anyone else who disagrees? If not, then we agree. We're all on the same page. Okay. So here's an example, a toy example. Then consider this with Z4, addition mod 4 given by this table. So the question is, what is the order of the element 1? I want to answer this so you can, because you have the table here, you can figure it out. Okay. So And then the other question is, what about 3, for instance? Okay, so you check the table. Okay, the table is here. That's why I put it there. And yeah, you check it, and you see what is the order. It surely exists. That's one of the things, because it's finite. You can check this. Okay, so I'll leave this as a question for you to try to answer by looking at the table. And by the way, try to find the order of the other elements too. Okay, like the 2, for example. Now, here's a second challenge for you. I told you I have a lot of challenges. Suppose that n is the order of G. Is it unique? Is the order of an element of a group unique? In other words, if n1 is an order of G and n2 is an order of G, does it follow that n1 has to necessarily be equals to n2? Okay, I'll let you to try to scratch your head and answer. Some of you already probably can answer this quick, but for the rest, it's very important for you to look at this and look at the definition first of all. And go through it by yourself before looking at a possible solution or asking someone. This is just a side note. Now that we are talking about exponentiation, right? So remember, in the semi-group section, we defined an element. This is just a side note. Sorry. We defined an element to be idempotent if it satisfies this. Now, the question is taking into account that in here, when we defined it, G was a semi-group. But now suppose that G is a group. And then the question is it true that the only idempotent element in a group is the identity? So the identity element is the only thing that can satisfy this in a group. Any flash memories, yes or no? I can also leave this as a point of scratching your head instead of giving the answer. Can anyone want to throw something on the thing? Okay, so Dimitri says yes. Okay, anyone else agrees with Dimitri? Or anyone else needs thinking?
I'm not so sure. I think you could have a non-identity idempotent even in a group.
In a group, okay, that's interesting. So I guess I will leave it as a thing on the study group session to try to prove whether this is it is the case that an element is idempotent if and only if it is the identity, or disprove it. Okay, so it's good actually to have like the thing Dimitri saying yes and you saying you're not sure, and possibly you could. Yeah, okay. Now, this is for the quantum computing guys. So if you are not in quantum computing, you're not interested in quantum, ignore this, okay? That's why I was saying this is the thing I decided to add this lastminute.com. So I hope I didn't make any typos. Yeah, okay. And for those of you who don't know what the unitary group is and these things, we'll come back to this in the matrix group section. But for those of you in quantum computing, especially those who've taken the foundation module, you know what the unitary group is. So suppose that G is the unitary group. Okay, for those in cryptography, this is not the unit, the mod. We will come to that. The unit, the group of the unit elements of mod n. This is not. It's not this. Okay, we'll come to that in the next session also, because we need that when we are talking about Diffie-Hellman stuff. Okay, this is the unitary group. So the group of operators on the Hilbert space C2. Okay. Now, the question is, let's suppose these, I hope I got the gates correct, right? This is kindergarten stuff. It will be embarrassing if I didn't get them. Quantum computing guys, correct me. These are like, we have the X gate, the Y gate, and the Z gate, right? Okay, so as per the definition, because, the definition of order was given on any abstract group, right? So the question is, what is the order of these gates, taking into account the thing as elements of the group, of the unitary group of U2. Okay, so this is a question. You don't have to answer it here. Go and think about it. Okay, oops, our friend Soham has already given an answer. Does anyone agree? What about the Hadamard? Okay, well, so Han also thinks, okay, for those of you who are unsure, this is actually good. You can go and think about it, yeah. Now, here's another trickier one. I'm not even sure whether I phrased this question correctly. Are all the unitary operators in U of 2 of the same order as the gates above, or they are just an exception? And if not, can you find examples of unitary operators of the same order as the above gates? Or I could also say of different order, actually. Well, let's do both. Try to find other operators of the same that are not these guys, but that are unitary of the same order, and try to find other ones that are not. Okay. Yeah, for those of you, this is why I'm saying this is just for the quantum computing guys or the physics guys. Sohang is a physicist. Quantum mechanics. He's bread and butter, so he knows this. Now, let's go to another thing. Let me just check the chat just to make sure. Yeah, so George is saying I think these are interesting matrices even without quantum application. Yes, definitely. We will come back to these guys in the matrix group section also. Yeah, not just in the context of quantum mechanics, but also in other applications like machine learning and so on. Okay, so now we need the notion of subgroup. Okay, I'm introducing it because this is the way I want to use to get us into the notion of cyclic group. So we need, and we'll take advantage to extract a little bit more on about to dive a little bit more on the subgroup structure. It won't be the last thing. We will keep coming to subgroups because there are other interesting subgroups that we will come across as we go along. Okay, so for the time being, let G be a group and H be a subset of G. Okay, so we say H is a subgroup of G if H forms a group, obviously under the same binary operation as G. Okay, so another much more clever way or much more formal way, or the thing that we could say is this: that H is a group if and only if these things hold. The identity is in H. The closure holds. So if you have H1 small h1 small h2 in H, then their product is also in there. And obviously the inverse of H has to be also in a thing of small h has to be in H, big H, okay? And obviously as a consequence, we have G, the group itself is a subgroup of itself, right? And the same with the trivial, this singleton, this made of the identity is also a subgroup. Now, here's a convention. If you pick a group theory book, you will see this a lot. So instead of writing, like in words, symbolically, we write this to denote that H is a subgroup of G. And when we want to be more specific, that H is a proper subset, a proper subgroup, we remove this thing, the equality sign here. We just put, we just write this, okay? But very often in abuse of notation, we just keep writing this, okay? When we talk about general, So, and here's a very interesting challenge. I think you can also do this, and it's very important for you to try. So suppose you have two subgroups of G, H1 and H2. The question is it true that the intersection of H1 and H2 is also a subgroup? Okay. The second question is, what about union? Their union. Is union necessarily a subgroup? Okay. If not, under what conditions, under what circumstances the union is a subgroup? Okay. So try to do this. If you are struggling, you can always ping me about proof. But it's just think it through. Go through this. This is where it's important to understand the thing. What do we mean with subgroup in the first place, and so on, and a bit of set theory too, right? What's intersection and union? Okay. So that's the challenge number 3. I hope I'm labeling the challenges. Okay. It's very important for you guys to go through this. Hands-on stuff is very important. This is why how the things will stick in the thing. Things will get into familiar to you with all this thing. Okay. Now, here are some of the special type of subgroup structures of G. The first one is this one, so given a group, we define Z of G is the set of all elements of G that commute with all the rest, okay? All the other elements of G. Obviously, this includes itself, right? Because every element of a group commutes with itself, right? So this is called the center, okay? This set is called the center of the group, okay? Now, I would say it's relatively easy to prove. It might be a bit time consuming that the center is actually indeed a subgroup of G, okay? And also, it's very easy to see that the center coincides with the group if and only if the group G is abelian, okay? I claim you should be able to see this also once you you look at this a little bit more in care, okay? So this is called the center. I think I'm not sure whether I think this is the British spelling, right, George? George is a linguist. The Americans write center.
Yes, but the Canadians also use the British spelling.
Okay. Okay. So sorry for our to you and the other our friends from America. Center. Well, sometimes it's like and here also, as you can see, instead of Z, in most books, because a lot of books are written by Americans, modern books, they will be like just replace the Z with the S. You should be fine. Okay, so this is the center of G. Now, there's another notion when we have H, a subgroup of G, this other set, C of H, which is the set of all elements in G that commutes with all elements of the subgroup H. So this is called the centralizer of H in G, okay? So the claim is this is also a subgroup, okay? You can also see this, I mean, this is like it's not hard to prove, all you have to do is to go through the the necessary minimal condition that this needs to be a group, right? The identity has to be so a group. These guys will show up later, especially in the matrix group sessions. Okay, so I'm bringing them forward because obviously we need the notion of a subgroup for what we are going to define in the next few slides. So I might as well just throw it. Okay.
So the center is the centralizer of the entire group.
Well, that's a question we can think for instance. Yeah, do they coincide? I'll let you scratch your head. Under what circumstances they would, for example, coincide? Okay, so again, for the quantum computing guys, this could be trivial or it could be like a trick. I don't know. See, try to go through it, and then you can say, oh, yeah. Okay, so let again G be the unity. The same. Now let H be the special unitary group. Okay, Alain, you also know this. Yeah, a lot of. Okay, so someone is saying the sound is breaking. Is that the case for you, George?
Yes.
Okay, let me check before I. Okay, let me check my VPN node. Everything is okay. What about now?
It's good now.
Okay. Okay. Do you want me to go back on the slides that I was on because you couldn't hear something, or you want me to continue? Did anyone miss anything?
I'm not sure about anybody else, but I was able to interpolate.
Okay, good. So Anyway, I was saying this is the second tricky challenge. This is only for the quantum computing guys. The rest can also, if you know what a unitary group and what the special unitary group is, you can try to to tackle this to see. So the main group is the unitary group, and the subgroup is the special unitary group. Okay, so the thing is try to identify at least 3 concrete elements of the center of U. Okay, 3 elements of Z of U2. Okay. And also try to identify at least 4 concrete examples of elements of the centralizer of the special unitary group. Okay, at least 4 elements. Okay, try to identify them, concrete ones. And now this question could be tricky. It could be nonsense. Try to see. Maybe I'm trying to catch you up. Maybe not. Who knows? Let's see. Whether these the quantum gates X, the X, Y, Z, and H are in the center of U. And the other question is if any of the gates are also in the centralizer of the special unitary group. Okay. Well, if they are, then obviously they need to satisfy the condition needed for them to be there in the first place. So you have to verify. Okay. It could be none of this is true. It could be one of them is true, but the other is not. So, but you have to verify. This is just, I noticed this is like to motivate. I noticed the people coming from quantum computing background might be very boring for you. We're seeing a lot of example of toy groups and this type of stuff that has no resemblance with with the thing. So I decided to do this. So, okay. For those of you who, especially those who have taken the foundation module, there's a video. You can go back to the foundation module where we are defining. I think it's in the. I'm not sure which lecture was it. Do you remember, George, where we were covering matrix groups in the foundation module?
Oh, that's a long time ago now.
It's a long time ago. Yeah, I will find the link, the precise sections, and then I will paste it on Discord so people can refresh the meaning of this special unitary group and or the unitary group itself. We'll refresh on this also before we get to the matrix group section. We will refresh not just in the complex case, but also the real matrices. We'll the orthogonal group, special orthogonal group, and so on. We'll come to this. Okay, so Amir is asking why we are distinguishing the centralizer from the center. Well, look at the definition. The center involves the entire group, whereas the centralizer involves the subgroup. So imagine this is a proper subgroup of G, for example. Yeah, so thank you, Soham. Yeah, exactly what Soham is saying. Okay, so this is a challenge. I knew it was going to be very interesting. So, at least our friends from quantum computations are now very excited with this. I'll try to keep putting in some challenges. There's another challenge, a final one. It's not over yet. Okay, so I hope my sound is okay because I'm going to proceed.
Sound is better.
Yeah, okay, so now we will start with the notion of cyclic subgroup, okay? I think this is the best way to get us into cyclic groups as opposed to starting in the most abstract. So, giving a group, okay, G, and giving an element of G, we define this set, okay, this set with this notation, with this very interesting bracket, okay, to be the set of all the thing generated by by the powers of the integer, okay, so G to the power of all integers, okay. Now this is a subgroup. Okay, this is the claim. You can prove this. This is a subgroup. Just if you remember the definition of the exponentiation and the properties of them, I claim you should be able to prove this guy is a subgroup of G. Okay, and this is called cyclic subgroup generated by the element G. Okay, you will see in the next few sessions, not in the next one, we will actually generalize this to the notion of generating sets, where we don't have just one element, but we'll have a set with few elements, and then these will generate the group. But we want, the reason we are focusing on one single element is because this is what will lead us to cyclic groups, okay? So for the time being, just this, okay? So this is a subgroup, okay? It's called a subgroup generated by the element G, okay? Now, it's very interestingly, you don't need to prove this. This is the thing I'm telling you now. And if you want, I can give you proof of this. But you need to show me that you try to prove it first. But it's true that G, this guy, is the smallest subgroup of G containing it. Okay, so it's very interesting. So this is the smallest subgroup of the small g containing small g. Okay, and another thing, very interestingly, if the order of the element G is n, then you can actually write this. It becomes just this group becomes just the identity G itself, the power of 2, and so on to the power of n minus 1. Okay, so when you know that the order of the group is 2, you're for example, like Soham was saying, then you should know the thing. You should know how to generate the cyclic subgroup of it. Okay. Okay. So that's very, very handy, because you know the order of it. You will immediately know how to generate, how to construct this cyclic group. Okay. This is the beauty of it. Now, here's an interesting challenge for you. Is it true? This again, I claim you should be able to verify this by looking at the properties of the thing that we went through with, you know, okay, of the exponentiation stuff. Okay, so is it true that the cyclic subgroup generated by G is the same, is coincides with the cyclic subgroup generated by the group inverse of G? Okay. Okay. So that's the first question. The second question, is it also true that the cyclic subgroup of G is always abelian, regardless of whether G is abelian or not? Is this the case or not? Well, try to find this. Okay. Here's a simple, some simple examples. For example, in the integers, the cyclic subgroup generated by 2, the integer 2, is this guy here, okay? Which is this, we write this, okay? Now, consider this, again, this is, I think we have the table in the previous slides. Z4, again, with the mod 4 addition. Then the claim is that the cyclic subgroup generated by 1 is this guy here. And the other question I leave you to you to scratch your head, obviously you will be able to confirm this by looking at the table, okay, is whether, I mean, the other question is, what about the cyclic subgroup generated by 3, by this element here, okay? So again, I'm very confident that you should be able to see this, okay? Now, for the quantum computing guys, I told you it's not over yet. I have a lot of challenges for you. So the challenge is to construct the cyclic group generated by the quantum gates, you know. So Soham was telling us that the order of the gate is 2, then it's very easy to generate this guy, right? Because of what we are just saying before. Because if it has order, finite order, then it should be of this form, okay? So this is like a piece of cake. If it's true, saying you can thank Soham, don't thank me. But you have to verify whether you agree with Soham or not. You will see, actually, just as a side note, when we talk about generating sets, you know, a set containing, you know, the X gate, the Y gate, the Z gate, and so on, will generate a very interesting group, actually. We'll see this at some point. Yeah, but that's when we are talking about generating sets, okay? As opposed to generation by single element. Instead, in this case, we are talking about generation by a set. It could be a finite set, for instance. Okay, so we finally get to the cyclic group structure. Okay, So a group is cyclic, a group G is cyclic if there exists some G, at least some G, at least a G, such that the group coincides with the subgroup, with the cyclic subgroup generated by such a G. Okay, so that's it. We say in that case we say G generates the group G, or that G is a generator of G, of big G. Okay. Now here's a simple concrete example. Okay, when G is equals to Z, the additive group of the integers, the claim is this is cyclic. So I'll already give you a heads up that this is a cyclic group. Now the question is, which of the following integers is a generator for Z? Okay, so let's go through it one by one. I will help you with this one, and then if you have any doubts, you can think. So is it 0? Can it be 0? Can 0 generate the integers? No. Okay. Okay, typo. I knew cyclic. Did I put what is the typo? Okay, yeah, I see the typo. Yeah, in here. Okay, this is not this is a silly typo, not silly cyclic type. Thank you. I will try to amend it before I upload the slides. Yeah. So 0 cannot be. Yes. Does anyone else disagree that 0 cannot be a generator of Z? Okay, so no one disagree. Excellent. What about 1? Is 1 a generator? Okay, so our friend Sohan says yes. Okay. Anyone goes with Sohan? Yes. Claudia also say yes. Diego say yes. Okay. Wow, everyone is saying yes. Yes, it's true. Yes. So 1 is a generator. Yeah, so everyone is yes. Okay. What about 2? This is just to confuse you. Let's see. There are more options. We'll see if there are. What about 2? Okay, 2 is not a generator. Yeah. So is Fernando saying 2 is a generator of Z? No. Yeah, no, it's not. It's not a generator. Yeah, it's not. What about minus 1? Okay, so Fernando is saying interesting. Minus 1 is not. Who agrees with Fernando?
I disagree.
Okay, it's a very interesting case. Actually, it's a very tricky one. They think for the first time. Yeah, yeah. So Dimitri thinks it is a generator. Yes, it is. So for those who are having doubts, you can actually go back to it and maybe come to the study sessions and interact with the guys. Those who think it is. So maybe they can explain you why it is. You know, looking at the definition, go back again to the definition of generator. You know, especially go back also to the convention of us. You know the convention we did on the thing on the additive notation stuff. This will help you see this. Okay. Okay, so it is indeed. So the story, the reason I gave these examples is to show you that a group doesn't need to have one generator. It can have more than one generator. Okay, you can even ask how many and these things. This is not something that we want to answer now. How many generators are there and so on. You know, so this is not a question to be answered today. But indeed, a cyclic group doesn't need to be generated by one single element. Okay, so now. Another thing I want to call your attention is this. Now, suppose that G is the additive group of the even integers, okay? Like this, okay? This is cyclic also. We have seen, I think, some of the example, there's one example when we were defining this thing before in the slide, it gives a hint already. So this is a cyclic group and it's generated by 2, right? Now, what is very interesting is that it is obviously a subgroup of the cyclic group, of the bigger cyclic group of the integers, right? So this motivates this question that I won't answer if you don't find the answer during, before the next session. We will find out the answer in the next session. Whether every subgroup of a cyclic group is cyclic. And there's also a typo here, cyclic. Sorry for that. Okay, so this is a question for you to try to detect whether every subgroup of a cyclic group is also cyclic. Okay, or whether Z, the additive group of the integer, is just an exception, happen to be an exception, whether this can be generalized. Okay, sorry for the typo. This is a cyclic. I will update the slide and correct the typo. So that's it. I didn't want to hit you with much. One more challenge that I have for you is this. Okay, under the normal additions, the normal addition, right? The plus addition that we learn how to sum up rationals and the reals and complex numbers. If any of them can be a cyclic group, this is a bit tricky. I just want you to go and think about it. Yeah, we will come back to more examples, Soham, in the next session. More examples like this thing. But yeah, you are right. You can you are suggesting other people to look at these guys to see whether they can answer like 3z, the multiple of 4, 4z, and these things to see whether it generalizes. Yes. But this is it for today. I think you have a lot of challenges to think about, and I ran out of time also to add more. But I think today you already start. We already have a little bit more than what we have been. The challenges is a little bit more harder, isn't it, George? Or is it all easier?
For me, since I've seen some of it before, maybe not so challenging, but I think
Okay.
for a beginner they can be, as we've seen by some of the disagreements in the discussion. That's maybe not obvious.
Correct. Mm-hmm.
So it's
What about
maybe.
you, Stefan?
So I think it's good to work it out if you have doubts.
Okay, so I am back again. Can you hear me? Okay, let me go. Where in the slides? When did you stop? I didn't realize I wasn't. Where in the slides? Maybe I need to go back again. Was it here or here?
I think this was the last one.
Ah, okay. Sorry for that. This is thing. Crowdcast is a little bit. This version is a little bit unstable. Sorry for that. Is there any particular thing that you missed? Thing? Yeah, we didn't miss any content. Okay. Was there any particular point? Yeah. Anything else you want to add, George?
No, yeah, I did see this slide with challenge 5.
Okay.
Oh yeah, we're good. I'm good.
So Barry saying you were challenging at the end about difficulty level. Oh yeah. So I was asking George. I think the pace is picking up the level of stuff. Even though, as George alluded, is because he's familiar with a lot of this stuff already, so it's not. But for someone new, for newbies, this will probably be a little bit more challenging so far.
It's important to use every part of the exact definition. Then it becomes easy. But if you overlook a part of the definition, then things can go wrong.
Yeah. Especially in the thing in the definition of the thing, right? This thing for like the order, for instance, it's a positive integer. Huh?
Yeah.
So.
Yeah. For instance, I wasn't clear. Although now that I think about it, it's true that you can have an infinite cyclic group.
Yeah. And you will actually see some very interesting result when you have an infinite in terms of classification at some point. You probably already know this. The thing is isomorphic to something. I won't say it. I won't spoil the party. Yeah. I think Soham is already hinting something. We'll come back to them next week. I mean, the week after, in the next session. It's okay. Well, at least the people know now what to think. This also means essentially that there's a when it comes to non-abelian stuff. So non-abelian groups cannot be cyclic.
It's good to have Samir and Soham and Amir and a few others back that we missed.
Yeah. What did I ask anything?
No, I meant that went here for the differential geometry part.
Ah, yes, yes. Okay, so is there any other comment before we the thing? I know we are almost on the hour, so not much left anyway. So this is it. We are starting to pick up the pace, and the plan, as I said, is to hopefully we'll still be with the cyclic groups in the next session. So we have what we need, the minimal, to give you a flavor of their usefulness in cryptography in the Diffie-Hellman key exchange protocol, how it works. We'll probably define, I think it's instead of just giving, I'll probably have to find a way of maybe start with the symmetric encryption. What do we mean with the symmetric encryption scheme, for instance? And then you will see. And then we take it from there, and then how do once you have that, how do you exchange the keys over a secure channel and this type of stuff, so there will be like some sort of the thing applied side of things. It will be theoretical, obviously, not like in implementation stuff. But you will have for those of you who never seen the stuff, or never heard of the Diffie-Hellman key exchange protocol, at least you will have a flavor about how interesting. And also the connection with there's a problem that especially some of you guys coming from computer science, the discrete log problem, so we'll touch that in the next session, because the Diffie-Hellman the thing, the hardness of it it relies on the hardness of the discrete log problem. So I mean the security of it. So in that case, I think nobody has any questions. George, any final comment? Anyone else wants to make any comment? If not, we catch up in the next session. And thank you so much. I would really final appeal. I would really like to have you guys, join me on the thing on the round table. So I will be emailing some of you to the thing. Those who, especially those ones showing up online, to see if you want to be part of the round table, so we can make it, as diverse as possible in terms of background and these things,
And I guess my last comment would be that I will try to hold a study session again next week.
Okay, that will be great. So I will set up the crowdcast again to see. I'll share it, and then you join. I will recommend, if it's you guys are having, if crowdcast is having issues, maybe you can just revert to Discord instead of taking time to think, because of these challenges. There are a little bit more thing for, especially for some of you new to these things. Okay, so Barry saying he's already registered. Sure, Barry, it will be great to have you on the thing round table to Great, thank you. I will be sending the thing, and then we can maybe have discuss the logistics of it and these things. I mean, we still have let's see, a few. So it will coincide. It will actually coincide with the next, the day after the next session. Yeah. So that's interesting. It means I have to prepare 2 slides, one for the thing, the other one for the thing. Yeah, but it's okay. Okay, good. So thank you so much, everyone. Thank you again, George. Thank you, everyone, for showing up today. And yeah, I look forward to seeing you in the next session. And yeah, have a good weekend. Okay.